I guess, the goal from our end. So what we're going to discuss now is gas EOR fundamentals. That's a discussion in general, which is both I guess, displacement relevant and also relevant for more mixing gas huff and puff processes. So again, we reiterate that miscibility in petroleum engineering is, at least in petroleum engineering space, we consider two types of miscibility: first contact miscibility and multi-contact miscibility. So for all practical purposes, when we have a set of we have some fluid at a particular reservoir temperature. We have a reservoir fluid composition that we denote ZI, and we have a particular set of injection gas composition, which can be, that can be CO2, it can be nitrogen, it can be water for that matter, or some hydrocarbon gas. The system could either be immiscible, it can be first contact miscible, or it can be multi-contact miscible. Immiscible simply just means that there's no pressure at where you're actually guaranteed to be single phase. That does not mean that you can't use that injection gas and a reservoir fluid and get a single phase mixture. So back to Bob's question a little bit earlier with regards to the swelling curves right here, where we had saturation pressures versus this vapor mole fraction, which you just think about it as GOR, where the axis is from 0 to 1. At this end right here, we only have the I guess the injection gas, and here we only have a reservoir fluid. And what will happen if you have something that's immiscible is that instead of this swell test coming up right here, you reach a critical point, then you get some dew points right here, and it flattens down, and you go down here, where you have a first contact miscibility pressure, or first contact. What will actually happen is that you get something that kind of explodes and goes up like this. So there are no first contact miscibility pressure, and you would say that these are first contact immiscible. And this is typical for lighter, if you use nitrogen or a very lean hydrocarbon gas, this is something you can see when you do that swelling test experiment. So doing a swell test, at least simulated swell test for your particular fluid system and injection gas, can, for an understanding reservoir characterization perspective, be very important before you do a gas huff and puff scheme. And we'll also spend some time today, and Stian will iterate on it and talk about this multi-contact miscibility concept. But again, we'll reiterate on the most simple thing to wrap our heads around, which is first contact miscibility. And first contact miscibility, as I mentioned one time already today, is the exact same process as when you mix carbonated water and orange juice, and you get something that at least probably me and all my friends have done that type of game in the kitchen when we were kids, and that's again what's relevant for huff and puff. And essentially the strict definition is that at any given pressure and temperature, first contact miscibility refers to the process in which two fluids mix in all proportions. And this is what's important. It's guaranteed that at any mixture of orange juice and carbonated water, as long as you mix them together, the resulting fluid will still be a liquid in this case, right? So at any concentration of either fluid, such that the resulting mixture remains single phase. So that's the strict definition. Multi-contact miscibility, however, is a more complex, process. And in a conventional displacement process, miscibility between an reservoir fluid and an injection gas develops through a dynamic process of mixing with component exchange controlled by phase equilibrium. So this is PVT, and this is essentially K-value related, which we introduced earlier, which controls component exchange, condensing, vaporizing mechanisms, and a local compositional variation along the path of displacement, That's essentially this conventional displacement process. And this, for many of you, will be a lot of words, and I acknowledge that. But for all practical purposes, what a multi-contact miscibility process accounts for is that if I am an injection gas that meets ejected into the wellbore, this is the first oil that I meet when I go into the matrix. What happens is that the two of us, mix together, and we create some new composition. And what happens is that maybe some of the components from the oil phase actually goes into solution with the gas, and maybe some of the lighter ends from the gas goes in to the liquid phase, and you develop and this is an equilibrium calculation, and these two phases would like to achieve thermodynamic equilibrium, such that after these fluids have contacted the first time in that pore space, you actually have a new reservoir fluid composition right here and an altered reservoir gas composition right here. And why is that relevant? Well, that's relevant because we learned that MMP is a function of reservoir temperature, injection gas composition, and reservoir fluid composition. So if we change the reservoir fluid composition and the injection gas composition, that means that the MMP of that altered reservoir fluid is different. And if this, we know that this gas guy right here, at least if it's two phases, the relative permeability and the mobility of gas is much larger than for the oil, so that will carry through and reach the next pore space, where a altered composition will reach this untouched fluid, and it's this dynamic multi-contact type of process, continuously altering compositions that creates this critical front that is created when you do a displacement process, and you have this multi-contact miscibility process developing. And it's a bunch of different mechanisms relevant for that we will discuss later as well. But this is a little bit, and if we did this course in person, I typically do this kind of game where I pretend that different people are different reservoir fluids and we are different injection gases and stuff. It's kind of fun, but obviously not possible to do virtually. But this is, I mean, if this is the first time you've heard about it, it is complex, but it's the one go-to paper to read is by a gentleman called Aaron Zick, and I think that paper was written in 1986. Isn't that correct, Stian?
Yeah, off the top of my head, I think that's correct. Let me check.
We'll add that to.
Yeah, 1986.
Yeah, and we'll add that to the material sent out after the course. But if you'd like to understand this complex, continuous dynamic process of constantly changing compositions, where you get this multi-contact miscibility process, that's the go-to paper by Aaron Zick. He has written one paper for SB his entire life, and then this paper he essentially has identified the most common mechanism, which is this combined condensing vaporizing drive mechanism, and this is the go-to paper, the most referenced paper in gas EOR displacement processes, and it was the first kind of a revolutionary paper that was at that time probably 10-20 years ahead of its time, and really good paper if you like to understand these things a little bit more in detail. If you like to only focus on gas huff and puff, however, it's not a requirement, but it's nice for your general understanding of miscibility and phase behavior, K-value determined processes. So we talked about this already. This is the second time I emphasize this, but I still think it is very important, and it's related to that minimum miscibility pressure is a function of different input parameters. This is equally true for first contact and multi-contact miscibility. So we need reservoir temperature, injection gas composition, and reservoir fluid composition, such that next time you go to a conference and someone talks about the minimum miscibility pressure, we know for sure that you can ask, okay, but what was the reservoir temperature? What was the injection gas composition? And can you say something at least generic about the reservoir fluid composition? Was it a black oil, a gas condensate, etc.? So for a given temperature, injection gas composition, and reservoir fluid composition, that minimum miscibility pressure is the lowest pressure at which first or multi-contact miscibility can be achieved for a specific process. So then the question is, what is MMP a function of? So now we've talked about it 2 times, and just to make sure that that this is clear for everybody, I would like everybody to write that into the chat, what MMP is a function of. This works much better live though, but let's just do it for the fun of it. And just to make sure that people are not sleeping in the morning here. So MMP is a function of 3 different things. Yeah. Yeah. So now it's just copy paste for a lot of people, I think. So and so it's totally correct that, and I think that's what many people say. It's the reservoir temperature. It's the injection gas composition. So a lot of people say something similar to this, but also some people use XI, and this is more, it's probably a little bit nitpicking on that. But the reservoir temperature is obvious. Injection gas composition is also obvious. But I would like us to be a little bit consistent when it comes to the usage of the symbol for reservoir fluid. Because when we use XI, then we typically refer to an oil or a liquid phase. But that's just, one of the cases. Because the reservoir fluid, if you have, let's say you have a fracture here, and you're looking at, some kind of element in this rock, I guess, we can essentially have 3 different cases where one can be a single phase oil. You can have a single phase gas actually, but the gas can have barrels in solution, so it can have a solution CGR associated to it, or it can be 2 phases actually. You can have XI and kind of YI there. So the generic way of just referring to reservoir fluid is using ZI consistently. So that's just a little bit nitpicking from my end, but very, very good, and everybody has understood that, so that's very good. And I mention it here as well with one example behind my scribblings. So reservoir fluid composition, a temperature, and just an example of a very, very rich injection gas composition right here. Any questions? No questions? Yeah. Good. We talked about this already, but now when I say it the next time or the second time, that's hopefully when it's super clear. Was there any questions?
Matthews, can I ask one quick question?
Yeah.
On slide 87, where you're defining MMP.
Yeah.
I have to look at my notes, but somewhere before you had mentioned, I think that's this definition which is in the books, right?
Yeah.
But I think you referred to something about 80 to 90% that it starts to mix or achieve that earlier. Do you want to remind us again what is that 80-90% you were referring to in the morning today?
Yeah, and that's related to what we see on the screen here about MMP being essentially a switch or a dimmer. So if you do a MMP experiment in the laboratory with a slim tube, for instance, experiment, that's kind of state of the art to measure multi-contact miscibility pressure, and we'll talk about that more later. Then what you do is to report recovery factor on the y-axis right here, go surface oil, and Stian, please step in if I'm doing this wrong. and right here you're reporting pressure, and then as pressure increases, your recovery factors are increasing until somewhere where you're close to, maybe 95 to 100%, where this curve is kind of flattening out. So around, I think, over 95% recovery, like the recovery factor is above 95%, and that's what we define to be the multi-contact miscibility pressure. When this curve right here and this curve right here is intersecting right here. So this is what we say is the MMP by multi-contact. So the definition is, okay, if we have a recovery of what's in the slim tube, which is just a porous media, is higher than 95%, then we've reached the miscibility pressure. And then the question can be, why is it 95% and not 100? In theory, on paper it should be 100, but in reality, also with a slim tube in the lab, you can have like physical dispersion and whatnot that leads it to be a little bit less than 100, but very, very high efficiencies. My point is that you can still, this is kind of dealing with the recovery process on like a pore scale almost type of or not on the macro scale, but call it in the porous media itself. So even though you are, let's say, when you are at the MMP multi-contact pressure, or when your pressure is that or higher, you're guaranteed to, in that pore space, have a recovery factor that's higher than 95% or more. While let's say you are at MMP multi-contact minus, let's say, 500 psi, then your recovery factor in the slim tube is still like 70-80%. Just as an example, which you can read out of this curve. So you're down here somewhere. It's probably a bad drawing from my end. Well, this is still extremely good. It's not perfect. It's not 100%, but 70-80% is definitely more than 20. And if you can't go higher for any type of constraint, you will be very happy with this. And also the other thing to mention is that this recovery efficiency or recovery factor number is just one of 3 things that contribute to enhanced oil recovery, call it efficiency, because you need to have also the volumetric sweep efficiency. So if you can't get the gas to obviously contact the oil and sweep through the media, it doesn't matter how large this recovery factor is. So if you have 70-80%, that's not perfect. It's not 100%. It's not above the MMP pressure, but it's still a very, very good result if you compare to maybe the recovery factor from primary depletion, which might be 20 or 30, 40%, depending on case.
If I can ask one last follow-up question, this won't be associated with your front movement, right?
Yeah.
In your reservoir.
Yeah. So this is associated with, and we'll show some more I guess simulation results and theory on this when we get to that topic. But this is related to displacement, but it's exactly the same in the huff and puff scenario as well. And we'll talk much more about that when we get to that part. But the main, I guess, thing that we need to communicate is that people think that they need to be at the MMP pressure or above to do gas huff and puff or gas EOR displacement processes in general. But that's not true, because it's more like a dimmer, where the closer you get to it, obviously the more efficient and good from a recovery efficiency standpoint it is. But it doesn't mean that from a financial perspective or an economical perspective, it does not make sense to do a scheme, or at least evaluate it and see.
Thank you.
Yeah, excellent. Was that about correct, Stian? At least 95% correct?
Yeah, I think you summarized it nicely.
a little bit. I mean, I haven't done that much interpretation of kind of slim tube results or that kind of determination, I guess. But that's at least a general idea of that. Another thing that's very interesting, actually, that comes up as a question many times is if MMP is a function of depletion. So let's say you have a well with a producing GOR through time that's maybe constant, and then you're dropping below the saturation pressure and starts to increase like crazy. And then when we're actually doing gas huff and puff, this is the producing GOR maybe at time of implementation, and we are going to take this particular sample, send it to the lab. Would this be a correct sample to send to the lab, or do we need to try to reconstruct this particular composition right here? The most important thing to emphasize there is that it's not really very, very important. And the reason is that, and you can simulate this and you can do it in the laboratory, but the MMP pressures, both the multi-contact, which is given in blue, which is lower than first contact, which in just this example, and the first contact miscibility pressure is not a very strong function of GOR or solution GOR. And that's what we're essentially trying to say here. So saturation pressure is going down. Saturation pressure means that you've dropped your liquid, your oil in the reservoir. That free oil saturation phase is lower. While the impact, it almost looks like this is a straight line. It's a little bit of a slope, but they are a little bit different. But for all practical purposes, they are the same. So don't try to over-engineer necessarily to have a representative reservoir fluid composition. And the reason for this is that, as I mentioned, the MMP is not a strong function on the GOR or the solution GOR, but what it's actually mainly a function of is the distribution of, call it, C5 plus components. So that's the distribution of those components that exist in your liquid. And these necessarily doesn't change that much during depletion. Of course, that depends a little bit on case, but in general, they don't down in the reservoir. These change much more during gas injection, but during depletion, they don't change that much. That's why if you look at, for instance, an MMP correlation, that MMP correlation is typically correlated to either C30 plus over C5 plus, or maybe the inverse of that, depending on which correlation, I guess. But that that this distribution of the components that are lighter than C30 versus the components that are C30 and heavier essentially can be used to generate a almost like a straight line in terms of MMP. If you plot the MMP by different mechanisms versus the C30 plus. So this is a little bit, maybe a little bit advanced and not necessarily very well explained, but what I'm trying to say is that MMP by first contact and MMP by multi-contact is not a very, very strong function of depletion. So use whatever reservoir fluid that you can sample and bring to the laboratory, and don't try to over-engineer that for that purpose at least. And these are just some values that we provided. You can see the differences there behind the scribblings. Yeah, so we learn a few key takeaways. And that's two different types of miscibility. First contact, which we'll talk more about, and multi-contact. And then we have MMP is a strong function of reservoir fluid composition. Here I used C30 plus versus C7 plus versus C30 plus, but it can also be C5 plus versus C30 plus. Really doesn't matter. Reservoir temperature, injection gas composition. And the impact on that MMP has on recovery is not a switch, but it is a dimmer. And that's very, very important to know, communicate to the rest of the technical community, communicate to managers and decision makers in general, in my opinion at least. And what you can do, at least if you like to do like a rigorous screening of your all the wells in your basin, for instance. Let's say you would like to do that, and you would like to do a very thorough gas EOR screening of what's important. In general, the plot you should make is something that we see on the plot in front of us. So it's essentially plotting MMP by first contact, which the lower the better. And then you also need to plot the formation volume factor. And here you actually see we have plotted formation volume factor for gas as well. That's possible to do if you take the dry formation volume factor of gas and divide it by the solution GOR, or CGR, sometimes also called the so-called large subscript V for vaporized oil ratio in like Eclipse and ResFrac and Harmony and whatnot. So this ratio gives you reservoir barrels per stock tank barrels, which is better when we go down here on the axis to the left. The lower this number is, the better, the more target. And the same goes for MMP by first contact, that we should go down here. So the stuff, the more we go down in this region, the better. And this is very, very quick thing to do for your wells, and would be very nice to, at least what we do for screening purposes. So when we are involved in projects, so increasing your efficiency down to the left. Yeah. And now this before we're going to jump to the next topic, we're gonna discuss some of these different conservation equations that I think also was a question a little bit later: diffusion versus dispersion versus convection. You know, how does that relate to mixing, etc. And we'll spend a lot of time on that. And I just wanted to make that clear before we go into that concept, that this is 100% clear to everybody. This is also from chapter 2 in the theory of gas injection processes by Lynn Orr, a Stanford professor, expert in gas EOR processes, that essentially defines convection, diffusion, and dispersion. And a little bit for fun, I like to call it confusion, because there's so many different terms for these things. But before we go further, I think it's important that we are 100% on the same page. And the same page I would like us to be on now is page number 7 in theory of gas injection processes. So what we can read here is convection is the flow of phase the flow of a phase carries components present in the phase along with the flow. A little bit difficult to understand, but this is also what's called advection. And in a petroleum engineering space, this is what we typically call, Darcy flow. So it's a flow essentially as a result of a delta P. And Stian needs to arrest me if I say something wrong. Diffusion, which is what we're going to spend a lot of time on here, is the random motion of molecules that act to reduce any sharp concentration gradients that may exist. Okay, so again, it can be a little bit hard to understand this sentence, but I always bring the train analogy that I learned from Kazumi up in Colorado School of Mines. That essentially says that Darcy flow, convection, or advection, this part right here, is essentially the train moving along the railroad, while the people inside of the train, that's diffusion. So the train is convection, and these guys right here and women, I guess, a little bit here. That's diffusion. And to make it even more complex, we have this process of dispersion, which is small-scale random variations in flow velocity also cause sharp fronts to be smeared. So this is related to displacement fronts. That was a question earlier. And dispersion during a flow in a porous media is always modeled as if it were qualitatively like diffusion. So from a modeling perspective, we model dispersion and diffusion in the same manner numerically. And Stian, that is on, and will do that part of the lecture, is going to go through these things a little bit later. Anything to add here, Stian?
Not really. We'll get back to all these definitions, and what the hardest part here is probably discriminating between what is diffusion and what is dispersion, because the word dispersion is very ambiguous. But we'll get back to that.
Yeah. But at least we know the difference between diffusion and convection is the train and the people within the train. That those kind of analogies I need myself to be able to understand these things. And for the purposes of gas huff and puff, what allows for mixing, that's essentially diffusion. So we hopefully, in the end of this, on the end of this slide, we got a little bit more clarity and a little bit less confusion, and that will also be the goal for the rest of the day. There was a few colleagues that actually gave me some critique in the break here, telling me that I should be more transparent in when we're going to have breaks, not just when it suits my own schedule. So what I suggest is that we take a break, this lunch break, in, let's say 40 minutes or 25 minutes. We'll take the lunch break, and that lunch break is 1 hour. And then after that, we'll go through the rest of the course and the rest of the slides. So that's just an FYI for everybody. Any questions here before we go further? Yeah, so we have some conference calls throughout the day. So what we are recording the course, so we'll send out links to the videos after the course. So if there's something you all need to revisit, just let us know, and we'll send that together with the course packages. So that's just an FYI on that topic. Okay. Good. So the next topic we'll discuss a little bit more in detail is again back to gas huff and puff. We discussed the process. This is the third time we see the schematics. But on a generic basis, that's what all the other operators are doing. Success rate varies, and it's highly dependent on fracturing, injection gas volume, pressure buildup, confinement, reservoir fluid type, geological setting, etc. So fairly complex. At least we haven't maybe convinced you of that yet, but what I hope to convince you all is that to really have an efficient huff and puff scheme, you need to have created, what some people, we call it a shattered rock or a shattered volume of rock. Some people maybe call it a stimulated rock volume, which not in all cases are the same, but it has to be surface area that allows for gas to mix in contact with reservoir fluid and oil. It also requires careful planning regarding injection fluid, injection pressures, etc. If you don't know the basic PVT that goes into that, that's the most important thing from a recovery perspective. So that's absolutely critical. And for those that have been maybe exposed to conventional gas EOR floods, it can seem like a very inefficient usage or utilization of gas, where we essentially just pressure up a reservoir and then we actually depressurize it, and we don't try to keep it at a high pressure. To try to give all of you a mental image of what do we talk about when we talk about a shattered volume, rock volume, a lot of different mental pictures from that. For those of you who know my friend Kevin Ratman, he wrote together with a bunch of other people from ConocoPhillips very, very good papers where they're sampling a EOR SRV in 2017 and 19, and probably had a paper this year as well. There they show essentially how many fractures that are created during pre and post completion, the spacing between fractures, they count fractures, etc. So there is no doubt that we're creating a lot of smaller fractures with the modern completions, and that's also seen in the hydraulic test sites and whatnot in the Permian as well. So it's not necessarily just a basin related thing. So this is just a mental picture of what we call a shatter volume. That's an absolute, prerequisite. And what we'll see actually from, if you analyze production data, you can actually, by just looking at the transients from the puff period, have evidence for that there is a shattered rock volume, and we are not actually producing from these pure planar fractures that we typically, or sometimes at least, model these reservoirs with. So it's a combination of smaller fractures and complexity and some fractures, and we'll get back to why, or you can ask that question, why that's the case from production data. So by a shattered volume, we're referring to a rubbleized zone around the hydraulic fracture with small blocks / pieces of rock. And before we actually go in and test, or do some type of analysis, we don't actually know whether this exists or to what extent it exists. But the only thing we know from simulation, from rock experiments, etc., is that no shattered rock volume means no huff and puff recovery. So this is an absolute prerequisite for that. Different ways of potentially quantifying it. There's a lot of different suggestions. We mentioned one already, sampling an SRV. We can do history matching. At least it will give you some balance. We can probably do geomechanical modeling for the ones that are in that space. People in the seismic space say that at least they can give you an indication of that with microseismic. I'm not an expert on any of these. Some people say that they can use RTA to back calculate this. There's probably some other things as maybe fiber and more these type of things can be used. Anything to add to this list, Stian, of different ways to at least maybe get an idea, order of magnitude of how much of that reservoir volume that is call it shattered, or at least available for mixing?
No, I think you summarized it quite nicely.
Good. Again, gas huff and puff is not a displacement process. The key mechanisms behind developed miscibility that's found in conventional gas injection literature are less relevant. So the main objective is not to displace oil from a producer to an injector, but rather for the gas to contact and mix with as much oil as possible, leading to two potential, at least key recovery mechanisms, which is dissolving / vaporizing oil components into the gas. That's what we call vaporization, the opposite of condensation. Or if we have single phase, it's what we call pure mixing. This is the dilution process. This is the saltwater, freshwater mixing. And good. Now we also have a great small quiz again, just to make sure that everybody is still awake. So the question is, MMP by first contact, how do we actually measure that? And everybody should write in the chat, and you get bonus point for being quick. So how do we measure first contact miscibility pressures? Yeah. Swelling test, slim tube, Slim tube, swelling test. Okay. So we have a few suggestions. Swelling test. Yeah, 4 different types of suggestions. The correct answer is a swelling test. Swelling test gives us MMP by first contact, while what gives us the MMP by multi-contact is slim tube. So that's good that we did that exercise such that that is crystal clear. And like the slim tube experiments are extremely expensive as well, so just make sure that you don't waste money on that if you're going to evaluate gas huff and puff. Very good. So what is a swelling test? We talked about it and we showed it earlier. But what you do is that you start with the reservoir fluid. So you sample a reservoir fluid and you plot the saturation pressure on this axis right here, on the y-axis. And on this axis you plot the vapor mole fraction of the injection, or the mix of injection gas that is in the call it resulting mixture of oil and gas. And what I mean by that is at 0, when this number right here is 0, we're only having a reservoir fluid, and it's only the reservoir fluid. And the first point that we plot here is if we're talking about a bubble point fluid, that's just the bubble point of that particular system. So let's say you've sampled something above the saturation pressure before the GOR started to increase. Then the first point on the swell test is just the saturation or the bubble point of that particular reservoir fluid. Then you, for instance, go in and you take that reservoir fluid and you mix that reservoir fluid in the PBT cell such that you have such that Fg is equal to, let's say, 20%. That means that the moles, the total number of moles in the cell versus the moles of the injectant in that cell, and if you do this fraction right here, you should get 0.2 or 20%. And then you take this mixture and you do a CCE experiment to measure the saturation pressure, and maybe we get a second bubble point, but then this time it's a little bit higher. And then we might do that for 0.4. Maybe it's still a bubble point right here. And then we do it for 0.7, and we see that the curve is starting to flat out, and now we're actually measuring a dew point right here. Then we know that the critical point is somewhere between these two lines right here. Maybe we do a second point on the dew point curve with even a higher injection gas to reservoir fluid ratio. And you can, with an equation state model, simulate these data points such that you get a smooth curve, or you can just draw the curve through the different points that you get from the test directly. The point over here should be the dew point of your injection gas. At TRES. So that's how they measure that. And the first contact miscibility pressure is just the tangent or the highest pressure on this particular curve. So this, whatever this pressure is the MMP pressure. So this is around 5,500 psi right here. So key takeaway 1, the gas huff and puff process is not a displacement process. It relies on the ability for injection gas to mix with the reservoir fluid. And mixing happens in near available region. where rubblization of rock is necessary to achieve significant mixing. Key takeaway 2, huff and puff is most efficient when injection gas and reservoir fluid are miscible. This can be achieved fully. Yeah, this is actually wrong. Instead of miscible here, you can make your own note. Single phase instead of miscible. This can be achieved fully when MMP is, or the injection pressure is above the MMP by first contact, so in this region right here. Or partially when we're below, but we're still above the saturation pressure. That's indicated here. Yeah, and we can measure that or calculate that for performing a swell test. This partial part right here is essentially the key reason why you can still have a very efficient process even below the saturation or the MMP by first contact. Anything to add here, Stian?
No.
Yeah. Good stuff. So now we're going to look at 2 different examples. So let's say we do pressure cycling at these different points. And in the pore space, in this case, you know, there's 0.2, or it's 20% injection gas versus reservoir fluid, while here it's 80%. So the maximum recovery efficiency is when this is single phase, which in this pore will be from 8,000 down to 3,000. While in this particular case will be from 8,000 down to 5,500. So the pressure cycling interval with high efficiency is higher in this, or call it all the pores with this ratio. Yeah. I think this is a good place to take a break actually, and then we'll continue from here in 1 hour. Would that work for you, Stian?
Yeah, that's perfect.
And from here, we'll probably go more through maybe the combination of simulation, flow, diffusion, dispersion, and these type of things. And I think we have probably around 100 slides more left to go.